articles in the reputed international journals. He also presented his work as an oral and poster in several national and international conferences and workshops. He has received several awards like Best Poster, Best Oral, and Best Thesis awards for his research activities. He was honored with I.A.M. Young Scientist Award 2024 from International Association of Advanced Materials, Sweden, in recognition for his contribution to electronic magnetic optical materials. He delivered several popular talks among the UG and PG students. We are very much privileged to have him with us today and looking forward to his insightful address. We welcome you, sir.
Thank you very much. It's my I am very thankful to the organizer for inviting me to giving a talk in this third international FDP on advanced functional materials. So I am going to today talk about the underlying magnetism in double perovskite oxide compounds. During this talk, first of all, I will talk about something basics about magnetisms and then some oxide compounds and why double perovskite compounds are important. And if time will permit, then I will show two of my research articles through which I have worked in these systems. So before presenting, here is my brief introduction. Already, Madam introduced me, so I am not going to dictate anything here. And next, last year I have received this I.A.M. Young Scientist Award 2024. And now let's move to the layout of this lecture. So first of all, I will give a general introduction of the oxide compounds and the basic magnetism in double perovskite oxide compounds. Then after the first next part will be I will discuss about the role of 3D 4F exchange interaction and anti-side defect in the double perovskite holmium cobalt manganese oxide, which shortly HCMO. Then after I will try to cover magnetic and magnetocaloric properties of double perovskite PR2 FeCrO6 compound. And if time will permit, I will show my new work on these complex critical exponents in order double perovskite ER2NiMnO6 compound, and finally conclusion. So general introductions part, first of all, I will discuss about what is oxide perovskite structure. So this structure basically represents oxide perovskite structure. It was discovered in 1839 by Gustav Rose in CaTiO3 material. So here your titanium ion will be in the center position and oxygen will be surrounded by this titanium position, titanium ions, and calcium is placed in the corner. So this is the basically main structure of oxide materials, which is in the form of perovskite. And the compound also got its name perovskite from the name of Lev Perovsky. Next, the question will come why the oxide materials are important. So first of all, they are important because they are low cost, cheap, and easy to produce. Then after they are chemically stable because we don't require any inert atmosphere to stable these types of compounds mostly. They are eco-friendly, energy efficient also. They are non-toxic, which is very useful, and they have vast potential applications from magnetoresistance to magnetocaloric effect and polarizations. Very vast properties they have shown, and depending on those properties, their application also vary. So we can tune the properties of these oxide compounds to get our desired requirements. So these are very important materials. Next, I will discuss about the classes of perovskite oxide materials. So we already know that perovskite compounds having the general formula RTO3. Here R is the rarer ion, T is the transition metal ions, and oxygen is this. So in perovskite family, by varying the transition elements, we can got different types of oxide compounds like manganites, chromates, cobalts, cuprates, bismuthates, titanates, nickelates, ferrites, and all of these have different applications. Like manganese has your giant magnetoresistance properties. Cuprate shows high temperature superconductivity. So depending on different compositions, we can get different structures also. Because their structure varies from cubic, orthorhombic to hexagonal, depending on the rare earth ion and the transition elements. And this is their general structure, as I already mentioned in CaTiO3. So you can see here that only one transition element is occupied. If we combine two or more transition elements, mostly two, then it will become a double peroxide. That means RMNO3 plus say RNiO3. So it will become R2MnNiO6. So this will form a double peroxide. So several permutation and combination of transition metal ions like T, Mn, Ni, CO, Fe, etc., alkaline earth elements, ACA, SRBO, etc., BA, etc., and rare earth ions are responsible for several fascinating properties in oxide compounds. So their general formula is this, where you can dope rare earth site by any alkaline earth element, and then it varies from 0, 1 to 3. So types of perovskite structures. So one is single perovskite, which is I already told about ABO3 type or ABX3 type. Why ABX3? Because so all times it is not in oxide, it is also intermetallic compounds like McNi3, NiFe3, and etc. ABO3 is ferrites, manganese, etc. They have single perovskite. Next, we come to the double perovskite, where there is two transition elements B and B prime. So these are the examples. Next, we have triple perovskite, where oxygen is changes to 9. So at present time, research on this field is highlighting so much. So in perovskite oxide compounds, the strong correlation between lattice charge spin and orbital degrees can be observed, and by breaking the responsible symmetry, breaking the symmetry between this space charge and orbital, we get different properties, which is shown by Hong et al. In this journal very nicely. So the interplay among all these degrees of freedom generates different types of symmetry breaking patterns, and those patterns will fascinate some properties like various type of magnetic phases, metal to insulator transitions, superconductivity, Jahn-Teller lattice distortion, multiferrocity, etc. So now I'm going to highlight about the double perovskite compounds. So the study of double perovskite system was initiated parallel to the single perovskite system in the early 1950s. Fasla and Karippan independently carried out their review work with almost 2,606 double perovskite compounds. Because here we can vary the transition metal elements. That's why we can get several double perovskite compounds. So double perovskite compound exhibit insulating nature because there is no report till now to show metallic behavior. So they exhibit insulating nature with ferromagnetic transition, high magnetic entropic change, and fascinating magnetic phase diagram, and many more. So this is the general formula of double perovskite compound R2BB prime O6, where R2 is a rare earth element, which is 4F ions, and B and B prime are the two different transition metal ions, which are we known as 3D ions. Here we use 3D. So crystal structure of double perovskite compound is like this. So they can be classified into two categories, order and disorder. In order category, there is a rock salt arrangement type B and B primes cations can be observed. That means if it is say manganese, then this is nickel. Again manganese, nickel. So this is a rock salt type or a zigzag pattern can be observed in ordered structure. And the rare earth ion is sandwiched between this octahedral. Okay, and they obey the monoclinic crystal structure, as for example these two double perovskite. And there is also disorder double perovskite compounds, where we can observe the random distribution of B and B prime ions. That means in the same crystallographic positions, both the B and B prime ions will occupy, and they will obey the orthorhombic crystal structures. So Nd2 FeMnO6, Pr2 FeCrO6, etc. So here you can see in these two examples, I will discuss later also. In these two examples, Nd is occupying +3 valence state, cobalt is occupying or stable at +2, and Mn is +4. But in this example, Fe and Mn both occupy +3. So you can see that here for disorder perovskite structure, the valency of the transition elements will be same, but in case of order, the valency of transition elements will be different by +2. Next, in this arrangement of atoms, there is a problem, or you can say a obstacle is arise, which is known as anti-site defects. So its anti-site defects is the misplacement of B-site cations. Suppose here it is your say your B and it is B prime. So it is possible that it should also be a B. So B. So instead of B prime, it may be a B also. So a anti-side defect, it will create as a defect. So this defect will introduce here. The difference in the ionic radii of the B side cations should be high to form anti-side defect in the unit cell. And anti-side defect influence the physical properties of the system. So there are basically two types of double perovskite compound, order and disorder. There is a third one also, which is known as layered double perovskite compounds, and a very less research has been going on the layered compounds, because all compounds are not showing layer structure. So I am not going to discuss in here in details about the layer structure, but here I will take two examples for order and disorder crystal structure. So comparison between order and disorder double perovskite compounds, we will discuss how they are two different. So in case of order, the ionic radii of transition metal ions are not comparable with each other. But in case of disorder double perovskite compounds, ionic radii of transition metal ions are mostly comparable, like your iron and chromium. Next, they mostly exhibit monoclinic crystal structure. Means order double perovskite exhibit monoclinic crystal structure with space group P21/N. And disorder exhibits orthorhombic crystal structure with space group PBNM or PNMA. Here, number of anti-side defect and presence of antiphase boundary will be very less or negligible, and here it will be maximum because same atom can be placed in several positions. And dominance of ferromagnetic ordering has been noticed along with antiferromagnetic ordering of rare earth ions in case of order perovskite structure. But here mostly antiferromagnetic ordering is dominating in double perovskite compounds. Here lack of polarization properties, and here you can exhibit mostly of these compounds exhibit polarization properties. So these are the basic differences between order and disorder double perovskite compounds. Now I will tell about the basics of magnetism. So we all know that magnetism is an effect of quantum mechanics that is connected to electron spin and orbit. So in materials, electron can have either paired electrons or unpaired electrons, which has spins. So only materials with unpaired electrons demonstrate order magnetic behavior. Here order means they have magnetic spins, whereas materials with paired electrons exhibit diamagnetic properties resulting from spin cancellation. Okay, so I will show a figure which describes different classes of magnetism under application of magnetic field. So in case of diamagnetic substance, the spins are oriented anti-parallel to the direction of magnetic field. However, in case of paramagnetic substance, initially without any application of magnetic field, the magnetic moments will randomly oriented, and after application of magnetic field, they are oriented along the magnetic field directions. Then the most prominent is ferromagnetic, where the magnetic moments align parallel with each other in the direction of field. Or if you don't apply any field, although they will align along the field directions. In case of ferromagnetic substance, two magnetic moments will occur here, because here two atoms, two ions will responsible for two magnetic moments, and they are aligned anti-ferromagnetically, or you can say anti-parallel with each other. And in case of antiferromagnetic substance, the magnetic moments are aligned anti-parallel with each other. And depending on this alignment, the magnetic behavior or the magnetic properties of materials will change, and this changing nature will be observed in case of their temperature dependence of magnetization as well as your field dependence of magnetization data. Now we know that there is in case of oxide compounds, we have transition elements, rare earth elements, both are magnetic. So there is a competition between various interactions and exchange mechanism which will decide the magnetic ground state of the oxide system. And in most of the cases, the magnetic unit cell and the crystallographic unit cell are identical with each other. So as a result, one can visualize the spin configuration by considering the crystal structure like this. So this picture I am taken from my own thesis. So this is shows different types of antiferromagnetic structure. This is A.K.M, where you can see the same plane magnetic moments are aligned in the same directions, while the intraplane magnetic moments are antiferromagnetic. In C type of antiferromagnetic substance, you can see interplanar in-plane magnetization will be anti-parallel with each other. However, they are parallel or they are behave as a ferromagnet in case of interplane arrangement. And in case of G antiferromagnetism, all magnetic moments are you can see they are aligned antiferromagnetically, either this with this or this with this or this with this. And in case of ferromagnetic, all the magnetic spins will align along the field directions. And this is an interesting magnetic arrangement where you can see a zigzag pattern like this, where this pattern will behave as a ferromagnet. Means you can say the same plane jet motion will behave as a ferromagnet, while there is reverse plane behaves as an antiferromagnet. Means this plane and this plane behaves as antiferromagnet, but in case of same plane they will behave as ferromagnet. And this is observed mostly in oxide compounds, mostly in you can say manganite oxide compounds, where charge order is dominating. So in case of double perovskite compounds, a rich magnetism behavior has been observed due to the presence of 3D and 4F ions. Because here you can see the interaction takes place between rare earth ions and rare earth ions, which is antiferromagnetic in nature, and this is observed in case of both ordered and disordered double perovskite compounds. Then there is a possibility of having ordered interaction between rare earth ions and your transition metal ions. In all cases, oxygen will be act as a mediator. So in this case, there may be a ferromagnetic transition which is seen in ordered double perovskite, and an antiferromagnetic transition which is seen in disordered double perovskite compounds. There is also you can say interaction between the transition elements, and they are B2 plus and B4 plus, and this is your ferromagnetic transitions, and this is for order double perovskite. And if your transition elements have the same valency, then it will behave as a disorder. It will shows an antiferromagnetic transition, and it is an disorder double perovskite compounds. And there will be seen a B2 prime transitions and B4 prime transitions, which is an antiferromagnetic in nature, and this will happen mostly due to the presence of anti-side defects. So this is the basic flow chart of your magnetism in double perovskite compounds. Magnetism is in most of the oxide compounds such as double perovskite is generally governed by super-exchange interaction mechanism. So the super-exchange interaction mechanism was governed by Goodenough-Kanamori-Anderson rule, which is similar, shortly known as GKA rule. According to this GKA rule, the first GKA rule stated that there is a 180-degree exchange interaction takes place between two half-field. These two half-field orbitals is relatively very strong, and this will favor antiferromagnetism, where magnetic moments are aligned antiferromagnetically. This is the first GKA rule. And in the second GKA rule states that when a 180-degree exchange interaction takes place between a half-field and a completely filled orbitals via this represents oxygen, as I already mentioned, already occupied orbital takes place, then this result will favors a ferromagnetism, and this is relatively very weak. And there is a third Goodenough-Kanamori rule, which is states that there is a 90-degree exchange interaction between two half-filled orbitals mediated by two ligand orbitals is relatively weak and favors ferromagnetism. So this will also this transition or this interaction can also be observed in case of double perovskite compounds. Next, I will tell about the magnetocaloric effect and magnetic refrigeration. So magnetocaloric effect was first discovered by Emil Warburg in 1881. This scientist Emil Warburg, he discovered the magnetocaloric effect in pure iron, and after his discovery, the history is made by themselves. And this is a picture which represents the ideal magnetocaloric effect, and I am not going to detailing about this structure because this takes a lot of time, where heat exchange will take place in both in adiabatic condition and isothermal condition. So basically, magnetocaloric effect is the thermodynamic phenomenon which leads to the change in both adiabatic temperature and isothermal magnetic entropy change of any magnetic material under the application of external magnetic field. So here you can see two formula, which is your delta Sm represent your magnetic entropy change, and this is your adiabatic temperature change, delta T adiabatic. So these two give us the basic formula for calculating magnetocaloric effect of any magnetic material. So what is the advantages over vapor cooling compressor? Because it does not use any harmful gases like chlorofluorocarbon or hydrofluorocarbon, etc., and its efficiency will be very high, 30 to 50%. So for a good magnetic refrigerant material, we should follow some protocols, or you can say some conceived properties. It should have large values of delta T adiabatic and delta S, that is magnetic entropy change. And it has wide range of operating temperature. This is very important. Then it should have high values of relative cooling power or refrigerant capacity, and it has negligible magnetic field and thermal hysteresis. It should be cost effective and non-toxic, which is very useful for us. So we will try to get all of these criteria in our materials to check the potentiality of our material in magnetic refrigeration industry. Apart from these practical applications, from physics point of view or fundamental research, magnetic caloric effect will help to detect the feeble magnetic transitions, which can be observed in case of our normal temperature dependence of magnetization. We can observe some feeble magnetic transitions in case of from the magnetocaloric effect. In the construction process of complex magnetic phase diagram also, it is helpful, and checking the potentiality of any magnetic material for magnetic refrigeration applications. So these are the basic theories. Now I have choose two compounds. One is order, which is HO2COMNO6 HCMO. Another one is your disorder, which I will discuss in next slide. So why I choose this holmium cobalt MNO6, which is shortly HCMO. So it lower cationic radii help us to deform the crystallographic unit cell. That means if we place holmium instead of lanthanum, then it will deform our crystallographic unit cell. As a result, the exchange interaction between, or you can say the octahedral angle between cobalt and manganese will change from the ideal 180 degree, and this will help us to generate some versatile and exotic magnetic properties in the compound. Next one is one research paper on this article, that Newton powder deflection has been performed, and it shows that the ground state is formed by F-type ferromagnetic ordering with magnetic spins of cobalt and manganese 4 ions with 60% anti-side defect in the unit cell. And the holmium ions remain in the disordered state. So our goal is to observe the magnetic interaction in details between the magnetic sublattices, and also to check the effect of local anti-side defect for this HCMO system. In parallel, the report on magnetocaloric effect of this compound have not been reported so far. So our motive is to check the magnetism on this compound. And next I have choose another compound, which is PR2FeCrO6 PFCO, which is a disordered double peroxide here, because you can see iron and chromium comparable ionic radius. So Arya report shows that this compound exhibits a multiferroic behavior with ferroelectric to ferroelectric transition and P hysteresis curve, as you can see in these two figures. So this compound already exhibits a multiferroic behavior, as I told, and there is a transition of ferroelectric to paraelectric behavior, as well as P hysteresis curve. So this is very important from practical applications point of view. And there are several other reports which shows that this compound exhibits different crystal structure. Someone reported PBNM, which is orthorhombic disorder. Someone says P21N, which is monoclinic, and it is order also. And again, R3C is your hexagonal type. So this give us a chance to explore this material in details. What happened with this crystal structure actually? So detailed investigation on the magnetic and magnetocaloric properties, as well as the thermal variation of the magnetic crystal spin structure of the PFO system has not been carried out up to date publication date. Here I have mentioned magnetic crystal spin structure because the ferroelectric properties of this compound have been discussed. Although it has 3 magnetic ions, so the magnetic properties was not discussed before our publication. So we will try an attempt to discuss about this magnetism and show it here. Now come to the experimental details. So both the samples HCMO and PFCO had been prepared by solid state reaction method, the well-known solid state reaction method. According to this solid state reaction method, the rare earth oxide was preheated at 800 degrees centigrade for 12 hours. All of you know we should preheat the rare earth oxide overnight because it has a chance to have some moisture or carbon molecules. So we should preheat it before weighting the compound. Next, we take the stoichiometry mixture of all the compounds of this preheated oxide and transition metal oxide, and they are well grounded in presence of ethanol. Then after we heated this at 900 degrees centigrade for 36 hours. As a result, we will get a polycrystalline disorder form of this R2BB prime O6 sample. So then after we will again reground this, and after applying a hydrostatic pressure of 4.5 torr, we convert these powders into pellet of diameter 5 millimeter, and that plates are further sintered at 1300 degrees centigrade for 72 hours, and we got the resultant our polycrystalline HCMO and PFCO compound, and those compounds are now ready for investigation for further process. So here I must mention that I did not use any atmosphere for preparing the sample. This is in open air, or you can say the atmosphere is here. So no oxygen was supplied or anything to get this compound. So we have done the characterization part, which is done by using X-ray diffraction. So basics of X-ray diffraction shown in this figure, which is use Bragg's law of diffraction and lambda equal to 2d sin theta. So I'm not going to discuss too much on here. And we have carried out magnetic measurement by using Squid VSM, PPMS VSM from Quantum Design. And both of these instruments are present in SINP Kolkata. And there I have performed these experiments. Now I come to the results of my two compounds. What is role of 3D 4F exchange interaction and local anti-side defects in this magnetic and magnetocaloric properties of double peroxide HO2COMnO6 compound? Let's start. So we already prepared the compound. Now we are going to check its structural properties, which is XRD analysis. So this is a full Rietville analysis of the obtained XRD pattern at room temperature, and we can see that all the peaks, the black one, experimental data were well fitted with monoclinic crystal structure P21 and space group, and you can see the goodness of the fit. Here you can observe a peak at approximately around you can say 20 degree less, and this will reflect that our PPR compound is in order from. If you will observe a peak nearly 20, then 20 degree, then it will indicates that the compound will be on order monoclinic structure. And we have refined the lattice parameter, and we will get these values. Next, from this crystallographic data, we have constructed the crystal structure look like this. We can see that manganese and cobalts are in the Roxol arrangement, as I already told, and the holmium is sandwiched between the space of this octahedral positions. So from this picture, we can determine the bond angle between manganese and cobalt, which is come around 144.45 degree, which is deviated from the ideal 180 degree, which can give rise to several interesting, fascinating magnetic ground states also. And the octahedral distortion angle, you can see this is not perfect octahedral, this is something tilted. The cobalt is tilted like this and manganese is tilted like this. So what is this tilted angle, average tilted angle, or you can say the distortion angle? That can be that can be calculated by using this formula, and it will be come around 17 degrees. So it's too high. In ideal case it should be 0, but it is 17.78 degree. So this will give some fascinating properties. And by using this XRD data and this crystallographic structure, we can also determine the valency of these ions, which is known as bond valence sum method. And by bond valence sum method, we get the valency of holmium as 3.14, which should be ideal 3. Cobalt is 2.24, which should be +2, and manganese is 3.75, which is around your you can say +4, nearly close to +4. So this is the crystal structure of our SCMO compound. Next, I will discuss about the magnetic properties. So this is the temperature dependence of magnetization data, and this data shows that the system undergoes a ferromagnetic transition around 77 Kelvin due to the super exchange interaction between cobalt 2 plus and Mn4 ions governed by the second GK rule. Here in this region there is no effect of your rare earth ions. The rare earth ions start ordering after you can say 10 Kelvin temperature. Here rare earth ions start ordering, which is antiferromagnetically. And you can see our negative exchange interactions, and this is come due to the anti-parallel alignment of cobalt manganese ion and holmium ions. So this will come for this. You can see here I have written the negative magnetization is due to the 3d4f negative exchange interaction between the rare earth holmium spins and ferromagnetic mesh of cobalt and manganese for sublattice system. And details of this negative magnetization is already discussed in my this paper. Then after this is for a small field, then we check the magnetic behavior for various magnetic fields, and we can see that above your 1 kilostate magnetic field, the magnetization, the negative magnetization behavior is disappear here. And this is due to the application of magnetic field, which tends to align the magnetic sublattices along the field direction. So as a result, this negative exchange interaction will be weakened, and as a result our magnetization will increase. And you can see there is a deep there is a upturn. This upturn is due to the ordering, the start of ordering of holmium ions. And these are FCC and FCW data, and we can observe that there is a very or I can say the negligible thermal hysteresis between these two. So this is very good for potential applications, because thermal hysteresis means there will be an energy loss in this system. Next, I am discussing about the inverse susceptibility as a function of temperature plot, because this is very important to understand the contribution of magnetic ions. So I have used this modified Fourier's formula to calculate to fit the data. So from this fitting, I get a theta Tm, the temperature of transition metal ions around 77.4 Kelvin, which is near to our TC, and holmium around 11.7 Kelvin. So this will shows us a very good fitting. So from this fitting data and the extracted parameters, we can estimate the contribution of magnetic ions. So you can see the black curve is the total total magnetization data, and the blue one is for transition metal ions, and the red one is for your rare earth ions. So you can see at low temperature this holmium ions is dominating, but near the TC region the transition metal ions is dominating. So we can observe a strong coupling between 3d4f exchange interaction in the total magnetization of the system. Next, we will discuss about the isothermal magnetization data recorded at several temperatures. So we can observe that this low temperature data shows a very well defined hysteresis curve. So it supports us the ferromagnetic behavior of the compound, and with increasing the temperature, the system converted into a completely straight line like behavior, and it resembles with almost a paramagnetic state. And we have seen that the octane saturation magnetization for this compound is around your 15.28 μb per formula unit at 70 kilostate, but we have expected that the saturation magnetization is around 26 μb for fully ferromagnetic alignment of all the three magnetic sublattices. So this reduction of saturation magnetization is possibly due to the presence of anti-side defects, which I will explain in explain in many cases. Next, I am discussing about the magnetocaloric properties. So to study the magnetocaloric effect, I have taken several magnetic isotherms at different temperatures, and you can see in the low field region there is a good behavior, or you can see a crossover of magnetization data. So for low temperature, the magnetization increases very sharply. But as soon as you increase the temperature, the magnetization increases very slowly, or you can say the slope is very less. So this will very good for to get a high value of magnetic entropy change. And so by applying this formula given by Maxwell thermodynamic relations, we have estimated the magnetic entropy change, and these are the values or the graphs for magnetic entropy change of this compound. So from this data, we have constructed this graph by using this formula, as well-known formula. So we can see three different transitions in this compound, or three different peaks. The first one is for the three. The first one is for your T at holmium, which is due to the active polarization or active orientation of holmium ions. Then after, the next peak will be at 3DF. This is due to the 3D and 4F axial interaction between holmium and cobalt, cobalt and manganese ferromagnetic mesh. And the last one at nearly at around 80, or you can say 77. This is the ferromagnetic interaction between cobalt and manganese core ions. So these three transitions shows us how rarer ions orient independently. Say then after your transition metal ions also orient ferromagnetically, and there is a interconnection between these two as a 3D 4F X interaction, and this is also this shows a signature also in the magnetocaloric effect, and this signature is hidden in our temperature dependence of magnetization data. Although we get a peak, but we can't justify the peak for what. So from this graph, we can justify that this is arise due to the 3D 4F axial interactions. Then after we have observed some negative magnetizations, negative magnetocaloric data here, which also known as inverse magnetocaloric effect, and this is up to your 10 kilostate field, which is also resemble with the magnetization data. So in this region, the antiferromagnetic axial interaction between holmium and transition metal ferromagnetic mesh is dominating at low field regions. So this data can also be correlated with our ZFCW empty curves. And we have also calculated the estimated the theoretical value of entropy change by using this formula, which is around 13.4 joule per kg Kelvin. Sorry, which is 37 joule per kg Kelvin, but our experimental data comes around 13.4 joule per kg Kelvin. So if everything is perfect, everything is okay, then why this data will come very low? There will be different. There will be possible reason. One is for incomplete polarization of magnetic ions. That means holmium ions is not fully saturated. If it will be fully orientated, then we will achieve a spontaneous magnet or a saturation magnetization around 26 μb per formula unit, which I discussed in my last slide. So maybe there is a incomplete activation of these holmium ions at this low temperature region, and there is maybe a sufficient amount of local anti-side defect present in the system, which can reduce the value of delta S. We did not have any probe at this moment to check how much anti-side defect is present in the system. So we can just assume that there should be an anti-side defect or inactive polarization of the compounds. So from this study, I can conclude like this, that fundamental requirements like high value of delta S max, although the value is less compared to the theoretical value, but it is high related to its nearby compounds. Then also moderate value of cooling capacities, which I calculated in this graph, is approximately around 280 joule per kg. So RCP we can calculate it from this region. And we can see the lack of thermal hysteresis in empty graph. So they all satisfied by the studied STMO compound, and it can be used as a promising candidate for magnetic refrigeration in the liquid nitrogen temperature limit. And the wide temperature span of is very beneficial for an ideal Ericsson refrigeration cycle. So we can conclude this part by in this note. Next part, I will discuss about the structural, magnetic, magnetocaloric properties of multiferroic host double perovskite PR2 FeCrO6. The previous one is for an ordered double peroxide, and this one is a disordered double peroxide compounds. So let's discuss and see. So you can see this is the crystal structure of this compound PR2FeCrO6. So in earlier I have mentioned that there should be a peak around your 20 degree small peak, but this peak is absent here, or I can't get this peak. So it will simply indicate as a disordered perovskite structure, and this whole XRD data is well fitted with orthorhombic crystal structure having space group PBNN. And from this XRD data, I have constructed the 3D Vesta picture of this crystal structure, and it looked like this. So we can see that both iron and chromium occupy the same crystallographic position. You can see clearly the half blue and half green. This represents your the occupation of the same two different atoms in the same crystallographic positions. And we have also calculated the average bond angle and octahedral distillation like earlier cases. Here it is come around 13.5 degree. And we also estimated the bond valence. We have estimated the valence state of these two ions, iron and chromium, which is approximately nearly 3. Now we come to the magnetic properties. So here you can see magnetization data taken at around 100 oerstate or 1 kilo oerstate. So first discuss this picture, the intermediate picture, 100 oerstate data. So in this data we can see sorry, the Virgin curve shows a negative magnetization. Virgin curve shows the negative magnetizations, and this data is due to the diamagnetic effect of this compound. Although it's magnetic, it's like diamagnetism behavior. Next, this diamagnetism behavior is due to the complex antiferromagnetic exchange mechanism between praseodymium 3 ions and iron chromium spins, resulting a negative value of magnetizations. Next, I will check whether these transitions this is due to the first derivative of this magnetization curve, which is known as dm by dt curve. And from this data, I have seen three transition point, and this is I already mentioned about the magnetic table of double peroxide compounds. So here we will try to resemble those transitions, those magnetic table with these transitions. The first transition I am considering here at Tn2, which is around 14 Kelvin, and this is at low temperature ordering of your praseodymium ions, where iron and chromium does not play anything. Next transition is very important, which is known as spin reorientation transition, and this transition is taking around from 143 Kelvin to 173 Kelvin. A 30 Kelvin window is required to complete this transition. What happened in this transition, or what does it mean by a spin reorientation transition? Because in these transitions, the magnetic moments of one spins is trying to orient in other crystallographic axis directions, and it can't suddenly switch from this to this in a particular directions. For that, it requires some temperature effects to, that means our temperature will give some, provide some energy now. So from there to there, it will take some time to transit. So here the spin orientation transition takes place between this interaction, praseodymium and iron chromium interaction. I will show it in figure in my next slide. And the last transition, which is we can observe here, you can see here, but by zooming this portion, we can see it. This is at Tn2 around 256 Kelvin. Here, the G-type antiferromagnetic arrangement of iron and chromium ion takes place. So basically, here we have observed three types of transitions at low field region. But when you apply a high field region, this negative magnetization is disappear, and the system behaves like completely antiferromagnetic in nature. So is there any conclusion come? Yes, with enhancement of field values, spin align along the field directions as a result of positive value of magnetization. And then after we have calculated the isothermal magnetization data. So here you can see, unlike the previous graph, here we can observe like a hysteresis. So here you can see mixture of hysteresis and also a what I can say a state-like behavior. So this is not a you can say well type of ferromagnetic phase or well type of antiferromagnetic phase. So this is a special characteristics of G-type antiferromagnetic, because in G-type antiferromagnetism, the magnetic spins are canted with each other, and this cantillation of the magnetic spins will result a weak ferromagnetic phase, and this weak ferromagnetic phase has been observed here. Here and above, you can see in this data 255 Kelvin, our transition of TN1 around 256 Kelvin. So when we have take the data around 255 Kelvin, this should be a straight line, but we did not observe. We observed a straight line, but we did not see any overlapping of field cooling and field heating data. There is a field hysteresis present in that loop. So it also resembles that there is a presence of weak ferromagnetic phase in this compound. Then after I have calculated the magnetic entropy change data by taking this isothermal magnetization at different temperatures, and this is the as calculated entropy change data, where we can observe the as mentioned transitions of this compound. So this low value of delta S may be due to the absence of long range ordering of praseodymium ions, and the existence of significant magnetic completion of frustration between the weak ferromagnetic and canted aeromagnetic phases may also be possible reason for such low value of delta S in the PFOC system. So here in this, till now, as a research scholar, as this workshop is also for research scholar, as a research scholar, I did not get an idea how to write a paper, because I did not get a high value of entropy change or high value of your magnetization, or not so much of significant figures. Then I have searched some Google articles and try to come about the generation of magnetic spin structure. And by using that concept of generation of magnetic spin structure, and by reading several articles, more than 100 articles, I am trying to develop the magnetic spin structure, temperature dependent magnetic spin structure of this compound. And you know this irreducible representation, mostly neutron powder diffraction pattern. When you analyze the neutron powder diffraction, these are useful. But I have not such too much sample or time to get the neutron powder diffraction data. So I utilize the irreducible representation of the literature of RFEO3 and RCRO3 system, and try to develop the magnetic spin structure for the present compound. So according to the crystal operation, at least 4 transition ions in a unit cell required to describe the spin configuration. And there we use 4 base vectors, vice F, all are plus, which is represent ferromagnetism, A up, down, down, up, again G up, down, I already told, and C type, this up, down, down. So these 3 represent antiferromagnet, and this is only ferromagnet. So these are used in 8 irreducible representation from gamma 1 to gamma 8 to decompose a 3D magnetic unit cell. But out of this 8, only 4 is utilized to design the magnetic spin structure of this ReFO3 and ReCrO3 system. So in this, you can see this is the 4 irreducible representation, gamma 1, gamma 2, gamma 3, etc. And this orientation represent the 4B side of this, how the magnetic spins or the atoms will orient it. Here it is mentioned. So if they are XYZ represent the crystallographic direction, unit direction. So here A represent this plus up, down, down, up, and like this way. So in this case, you can see XYZ all are orientated. So this does not carry any net magnetic moment. So it requires lots of time to understand and lots of time to practice it to understand how they are oriented. So I am this will be very tough for some of you. So I am skipping this part. And finally, for my sample, I have constructed these magnetic spin structures by my own hand without discussing with any collaborator. So in this region, the below this temperature, the system behaves paramagnetic. So here all the magnetic spins will randomly oriented. So I did not draw any structure. I have drawn in this region TN1 to TSR, where TSR will start. So here the system exhibits, I should give this one. So below T1, the order of iron and chromium ions is in G-type antiferromagnetic in gamma 4 configuration. So G-type antiferromagnetic will take place here, while magnetic moments of iron chromium spins lie along the A-axis. You can see here, if it is the A-axis, so magnetic moments are lying along the A-axis, but they are antiferromagnetically coupled. You can see there is no magnetic moment I have shown for posidonium, because at this high temperature posidonium will not active. So I did not mention this case. In the TSR region, this region, 30 Kelvin region, both gamma 2 and gamma 4 coexist together, where magnetic spins of iron chromium sublattices changes from x-axis or x direction to z direction. So initially it was in the a-axis, so it is trying to change to the z directions. So I am not completely showing that it is from this direction to this direction. I am just showing that it is now start changing from this to this direction. So in the intermediate, I have shown this picture. So here you can see there is a net ferromagnetic component present in the AC plane. Okay, but all those you can see, this is up, this is down. They are antiferromagnetically aligned, although. And below TN2, now praseodymium ion will come to the picture, and praseodymium ion will arrange in a C-type arrangement. C-type arrangement is what? Up, up, down, down. So they are antiferromagnetically aligned, although in plane they are up, up, down, down, which is signature of C-type arrangement. Okay, and at the same time, praseodymium ions already completed its spin orientation, so it is in the z direction. Okay, so this spin structure I have derived for this compound in 2021, and after 6 months, similar crystal structure was experimentally described by Wang et al. So this was a good prediction for my purpose. Due to the lack of time, I think I should skip this part also. Sir, am I audible? So I directly come to the conclusion, or I directly go to this part, just skipping. Here, I am discussing about the complex critical exponent, which is also used to describe the magnetic behavior of a system. And here I have taken the order double perovskite compound here to MnO6. So similarly, there is a motivation. I'm not going to detail lots of. And in crystal structure, which is also a order crystal structure, you can see again the peak is arise here. So it's an order crystal structure. Here we can observe a ferrimagnetic transition with application of field. This is gone. Then after this system also exhibit Griffith phase-like behavior. Griffith phase behavior is that above T, some ferromagnetic cluster will form in this compound. Similarly, this is isothermal magnetization, and I have extracted the ferromagnetic and antiferromagnetic part by using this function. We have also estimated the magnetocaloric effect and dictate the 3 different conditions reason, which I already discussed for SCMO compound. And for critical exponent analysis, I am taking some magnetic isotherms near my TC regions, and by using modified Arrow's equation of state given by this equation, we can determine the values of critical exponents beta and gamma, where beta describes how the ordered magnetic moments will grow below TC, and gamma describes the divergence of the magnetic susceptibility above TC. And after getting the fitting, we have calculated the values of beta and gamma according to Arrow's equation of state. The line which is close to TC will pass through the origin. So in this case, our TC will come around 76 Kelvin, and from all the fitted, whether power law fit or Kubel-Fischer method, we will get a nearly equivalent values of beta and gamma. And the third critical exponent delta can be calculated from the isothermal magnetization data, and this will come around 1.73. So you just here keep in mind that beta is 1.08, gamma is 0.765, and delta is 1.73. These three values does not follow any universality classes of magnetism. For a mean field model, this value of beta should be 0.5, gamma should be 1, and delta should be 3. But everything is deviated from the ideal value, where beta is close to the 1 and gamma is decreasing to the 0.5. Why this happened? This should not be expected for a universal magnetic behavior. So for to check whether our experimental data or our analysis is correct or not, for that we have used this magnetic scaling equation, and it shows two different branches, and it also shows that our obtained exponents are correct, and all the scaling functions also provide us that yes, the obtained values of our beta, gamma, and all are same. So what are the possibility we'll discuss later. Then after we have analyzed the heat capacity data by using your Debye and Einstein equations, and also estimate the magnetic entropy change from here. So you can see in this picture the magnetic entropy change obtained from heat capacity data and isothermal magnetization almost match with each other. Similar for delta adiabatic temperature also. And from this heat capacity data, we can also estimate the third critical exponent, which is known as alpha. And the value of alpha is 0.96, which is very, very high. Its value should always be less than 0.1. So why this will happen? So this is the summary of my all analysis about beta, gamma, delta, where beta is close to 1, gamma is close to 0.7, delta is close to 1.7, and is a third critical exponent, which I am not going to discuss, and alpha is 0.9. Alpha value is different. By using Rasbrook relation or Widom scaling relation, we can calculate. This picture will tell you everything. So you can see the red represent my work, and other represent the universal theoretical predicted values. So what will happen in this case, in my case? For your already reported data, the value of beta should not exceed 0.5. Chirality theory is different. I'm not going to dictate, or I'm not going to take anything from that part, because our sample theory and this theory is different. So mean field theory represent 0.5, and our obtained value is 1.088. Again, in case of gamma, tricritical and mean field value represent 1, and our value is less than. And similar for delta value can be go to up to 15, but our value is less than 3 also. So why this will happen? This will happen. The theoretical work is still going on. I did not get too much result, but as an experimentalist, I can predict that due to the presence of non-cluster Griffith phase. Okay, presence of non-cluster Griffith phase in the system. So after getting the theory part, I can come to the conclusions. And from there, I will draw the magnetic phase diagram of this compound. This is that. And here I represent the temperature dependent on magnetic spin structure, how magnetic spins will orient and changing their positions with this. So here you can see the ferromagnetic cluster of this is given, and antiferromagnetic arrangement of RBM moments also takes place. So this will show us how temperature changes and different magnetic phases and different types of alignment can be observed in this picture. So come to the conclusion of my talk. So the role of placement of transition metal cations in the unison and local anti-side defect on the magnetic and magnetocaloric properties of two different crystal structure-based double perovskite compounds, HCMO and PFCO, have been discussed. A strong correlation between holmium and these transition metal magnetic sublattices has been observed in the HCMO compound having monoclinic crystal structure. Additionally, we have constructed the thermal evolution of the magnetic spin configuration of the orthorhombically distorted PR2Fe-CrO6 system. Recently, Wang et al. Had experimentally proved that the thermal evolution of magnetic spin structures in the perovskite disk system, which are well matched with those we had predicted for the PR2Fe-CrO6 system. And the last one, the analysis of the critical exponents in the ordered disk compound shows that the obtained values of critical exponent does not follow any known universality classes of magnetism. And this is possibly due to the presence of quench disorder or antisight defect. And mostly I am thinking about the presence of Griffith phase in the system. Later it will we will know. So basically this lecture was based on these two following publications and some other works on double perovskite compounds from our research group is going on. So I acknowledge my supervisor, my postdoc mentor, and my all collaborator and DAE and SNP for funding and instrument facilities. Thank you.
Thank you, sir. Thanks for your enlightened lecture. Participants, if you have any queries, please unmute yourself. You can ask your queries. And if you wish, you can type your questions on the chat box. Participants, if you have any queries, please ask now.
I can stop the sharing.
Yeah, you can.
So is there any chat box?
Chat box.
Okay. Is there any question?
Any questions or feedback? Anyone wants to say your feedback?
Sir, me?
No, any feedback the audience they can give. Facility. Yes. So there YouTube does it. Just we have to check whether there is any question in the YouTube.
Okay.
No, there is no question in the YouTube also. So I think everyone understand your lecture nicely. Yes. Thank you. Thanks for your enlightened lecture, sir. So
Thank
we
you,
can
sir.
welcome the next speaker now. Thank you.
Sir.
Okay. Atique, give me 1 minute to give the introduction about. My colleague will introduce now. Okay.
Okay, so I never present in the Google Meet. I'm trying
yes,
to.
yes, you can start now. Thanks for spending the time. Actually, it is a night for you, around 1 a.m. Thanks for your spending the time with us. Just a minute, my colleague will intro about you.
Good morning, everyone. It is my honor to welcome you all for the second session of the fourth day, third international FTP on Advanced Functional Materials, Energy and Environment and Sustainable Development 2025. This FTP has been an incredible platform for faculty, researchers, and industrial professionals to exchange knowledge, share insights, and discuss emerging trends in functional materials that play a crucial role in sustainable development. Over the past days, we have gained valuable perspectives on innovative materials and applications in energy and environmental sustainability. Today, we are delighted to have with us an eminent speaker, Atique, who will be enlightening us on the topic robust synthesis of targeting glycol nanoparticles for surface enhanced environment based image guided tumor surgery. We are eagerly looking forward to a thought provoking session that will inspire new ideas and foster academic and research collaboration. On behalf of organizing committee, I extend my heartfelt gratitude to Atique for taking the time to share his expertise with us. Before we start the session, let me introduce Mr. Atique. He has obtained his bachelor's and master's at University of Chittagong, Bangladesh, Master of MPhil at Bangladesh University of Engineering and Technology, Dhaka, and now he is an graduate researcher at Department of Chemistry, Michigan State University, US. With a distinguished academic and research career, Atique had made a significant contribution in the field of material chemistry with the emphasis of advanced functional materials, energy storage devices, and sustainable technologies. He has published nearly 80 research articles extensively in high impact journals and has received numerous awards for his pioneering work. He has also been actively involved in many notable projects and industry collaborations, making a remarkable impact on scientific research. To name a few, he have got awards from Ministry of Science and Technology, Government of People's Republic of Bangladesh. He has guided nearly 13 students for their MS degree program. Apart from his research activity, he has been an inspiring mentor, guiding many young researchers and academicians. We are truly honored to have Atique with us today, and we look forward to an engaging and insightful session. Sir, the session is yours now. Thank you.
So thank you, the organizer, for inviting me. So thank you for the kind introduction. So I'm so sorry, I never used the Zoom Meet just to present anything. So I don't how so. I don't know what's going on. So I believe you cannot see my screen, right? Can anyone guide me how I can share my screen, please?
Yes, sir.
Because I never use the Zoom Meet to present anything. We are always using the Zoom.
You can go to the entire screen mode. There is a three dots will be there in this nearby from the hand.
Yes. Then
There is a three dot will be there, no, sir.
yes, three dot. Then
You can click this. You go to the full screen.
full screen. Okay.
Yes. You can click this.
Then can you see now?
No, you just click the full screen. I have not yet seen your screen.
I'm so sorry. Yes. So full screen. Then
Yes. No, not that. You can go to this one. Nearby hand, there is one arrow mark will be there. Present now.
yes, arrow present now. This one.
Yes, the upper yes. You can click this.
Select.
Yes. Yeah, the entire screen option will be there. The third.
Yeah, okay. Enter screen. Then share.
Click this and click inside that. Click inside and share.
And I don't know what is going on.
Yes, it is coming. Now you open your PPT.
So yes,
Yes, go to the full screen mode now.
you can see now.
Yes, you can change now. Yes, fine. Now you can present. No issue.
Okay. Thank you so much. I'm so sorry. I never present in the Google Meet apps, so we are using always the Zoom. I'm so sorry for the interruption. Okay.
You can take.
So hello, good morning, everybody, and thanks the organizer for inviting me, and thanks the chair for the kind introduction. So now I'm talking about one of my research projects, that is the robust synthesis of targeting glyconanoparticles for the surface enhanced resonance Raman-based image guided tumor surgery. Before going in details of my research, I want to show what is the background of my research. So we know for the usual tumor surgery, the physicians are doing the visual and the point option. Yeah. So usually for the removal of the tumor, the physicians are following the visual and palpatory detection. But if you do the visual and palpatory detection, it is difficult to remove the whole tumor. So there is a possibility of remaining the positive margins here, which is also known as the residual markers. And these residual markers can also lead to the growth and metastasis. And it can, but if you add an extra imaging technique, which is SIRS, and SIRS is an technique which can detect the low level of the receptor. So if you add that one, then we can remove the whole tumors without leaving any markers here, and it is possible to remove the complete resection of the tumor. So that means just if we use only the visual and the palpatory detection, sometimes there is a possibility. And in the US, for the breast cancer, it is reported that almost in 70 cases, there is a possibility of residual markers present in the tumor. But if we add an imaging technique which is sophisticated, and using this technique, we can remove the complete tumor. So now let's see how Raman spectroscopy works. So we know, so whenever a sample is irradiated by a source of light, it can be reflected, it can be scattered, it can be transmitted, and also it can be absorbed. So in case of the scattering of the light, so the intensity of the light, incident light, and intensity of the scattered light may be the equal, and that is called the Rayleigh scattering. But if the intensity of the incident light and the intensity of the scattered light is not equal, that is called the Raman scattering. And it is reported that in 1 in every million photons is scattered inelastically. And this inelastically, already I mentioned that it is called the Raman scattering. So since 1 in every million photons is scattered inelastically, so the signal is very low. But the important thing is that we can see the peak width of the Raman spectra is 1 to 2 nanometer, which is almost 100 times narrower than the quantum dots or the fluorescence spectroscopy. So there's a possibility of less overlap of the spectral overlapping, so we can use the Raman. But already I mentioned that 1 in every million photons is scattered inelastically, so the signal is very weak. This signal can be enhanced by doing some techniques. That means if we put a molecule which is Raman active on the surface of certain nanoparticles such as gold or silver, the signal can be enhanced. And it is theoretically almost the signal can be enhanced to 10 to the 14 times. Since it is a surface phenomena, that means enhancement of the Raman signal by placing the molecule on the surface of metal. So that's why it is called the surface enhanced Raman scattering. So, and also the most important things of the surface enhanced Raman scattering is to do the multiplexing. So what is the multiplexing? So multiplexing means we can target multiple biomarkers in a single test. And if we do the multiple biomarkers in a single test, definitely the diagnostics can be better. So let's see how the multiplexing works. Suppose this is a gold nanoparticle. You can see the gold nanoparticles. Suppose we consider the gold nanoparticles. The gold nanoparticles is functionalized with 3 different reporter molecules. So that means, suppose these are the 3 reporter molecules, which I already just shown here as the tersen. And definitely each and every Raman active molecules has its unique spectral signature. When the gold nanoparticles is functionalized with the Raman active molecule, it is called the search nanoparticles. And the search nanoparticles is functionalized different types of the ligands. You can see this is the ligand, these are the ligands. So now we can see the gold nanoparticles first functionalized with the search active molecule, which is now termed as the search nanoparticles. And the search nanoparticles is further functionalized with the ligand. So ligand can target its own analytes. So now suppose we mix the 3 different search nanoparticles having 3 different reporter molecules and 3 different ligands, and we mix them together and we applied in a mixture of the analytes. We can see analytes. So whenever we mix all the search nanoparticles in a mixture of the analytes, so based on the ligand receptor interaction, suppose these are the receptors. So based on the receptor ligand interaction, the search nanoparticles can bound with their respective analytes. And whenever we apply the laser, we can see it can give us the signal based on the Raman reporter molecule. So then we can easily distinguish the analytes from the receptor ligand interaction. And from the search intensity measurement, we also can quantify. So this is the general phenomena, how the search nanoparticles can detect multiple biomarkers in a single test. Usually gold and silver nanoparticles just show this type of search properties. But in our research, we use the gold nanoparticles as a search substrate. Why we consider the gold nanoparticles as a search substrate? Because gold nanoparticles is chemically stable, and these are less prone to oxidation than silver. And also gold nanoparticles is biocompatible, and gold nanoparticles can easily functionalize through the gold-thiol interaction. And also, and it is already reported that 50 to 60 nanometer gold nanoparticles exhibit the maximum search intensity. So then move to the synthesis and characterization of the search nanoparticles. So the most common method used for the synthesis of the search nanoparticles is called the Tarkibish method. In the Tarkibish method, usually the gold salt, that is suppose chloroauric acid, is considered as the precursor, and the sodium citrate is considered as a reducing agent. So this is the most common method to synthesize the gold nanoparticles. But if we want to say, already I have mentioned that 50 to 60 nanometer gold nanoparticles shows the better performance as a search nanoparticles. But if we want to synthesize the gold nanoparticles of 50 to 60 nanometer using this method, it is not possible to get the nanoparticles with the uniform size. You can see from the TM image, so usually we cannot synthesize the nanoparticles more than 30 nanometer using this sodium citrate assisted method. Then we are searching how we can synthesize a uniform size of 50 to 60 nanometer gold nanoparticles first. Then we figure out that if we synthesize a 20 nanometer or 17 nanometer gold seed using the sodium citrate method, then we use tris base as a reducing agent, and it is possible to get the nanoparticles of 50 nanometer with uniform size. So in this synthetic method, we just use the boiling chloroauric acid solution. We add the sodium citrate. So first we synthesize 70 nanometer gold seed. Then in a boiling solution of the gold seed, we add, in a boiling solution of the trees base, we add the seed and the chloroauric acid solution, and we got 50 nanometer gold nanoparticles. And already I have mentioned that only sodium citrate assisted method does not give us the 50 nanometer gold nanoparticles with uniform size. So from these experiments, we can find out that the trees base assisted seed mediated synthetic method gives us 50 nanometer gold nanoparticles with uniform size. And this is the characterization you can see from the UBBs and DLS. From the DLS, already I have shown the TM images. And from the DLS, you can see there is a nice distribution of the 70 nanometer seed and 50 nanometer gold nanoparticles. And from the UBBs, you can see there is an increase of the lambda max, which is an indication of the synthesis of 50 nanometer from the 70 nanometer gold seed. Then we synthesize these search nanoparticles. Already I mentioned that the 50 nanometer gold nanoparticles, when functionalized with the search reporter molecules, we termed it as a search nanoparticles. Already I have mentioned in my previous slides how we synthesize the 50 nanometer gold nanoparticles. So this is also a one-pot method. That means when we are synthesizing the 50 nanometer gold nanoparticles, we can add micromolar level of the dye solution. Just we put it for 1 minute, and in 1 minute we find out that the search nanoparticles is formed. And this is the, you can see, so this is the S40 search nanoparticles. S40, this is the search flavor. It is for the dipyridine. So this is a commercial name. So we can see the, so this is the gold nanoparticles. We can see there is no aggregation or change in morphology happens when the gold nanoparticles is transformed to the now search nanoparticles. So from these few slides, we can confirm that we successfully synthesized 50 nanometer search nanoparticles through the trees base assisted seed mediated method. Then we just checked out the sensitivity of our search nanoparticles. Already I have mentioned one flavor, that is the S420. These are the other flavors. You can see we just synthesize search nanoparticles with different flavors: S420, S421, S440, S481, S493, IS780, and CI5.5. You can see this search spectra has a unique spectral signature. Then we determined the sensitivity of our search nanoparticles. We figured out that our search nanoparticles can detect the femtomolar level. That means our search nanoparticles is super sensitive. It shows the femtomolar level sensitivity. Then, so already we have synthesized the search nanoparticles with femtomolar level sensitivity. Now already I have mentioned that for the synthesis of the search nanoparticles, in order to apply them for the biological activity, we need to attach a ligand which can target the respective receptor molecules. So here, from this image, you can see that different types of cancer, suppose breast cancer, liver cancer, gastric cancer, colorectal cancer. So a lot of cancer cells have shown the higher affinity of the CD44 protein. You can see breast cancer has highest level of the CD44, overexpression of the CD44 protein. CD44, it is cluster of differentiation. It is a cell surface protein, which, so you can see, so that means this type of protein, CD44, is overexpressed in different types of cancer cells, such as breast cancer, liver cancer, gastric cancer. So this is the receptor protein. And this receptor protein can selectively bind with a polysaccharide, which is known as hyaluronan. And you can see hyaluronan can bind selectively with the CD44 protein. So what is hyaluronan? So hyaluronan, it is a glycoprotein. That means, sorry, it is a glycan. That means it is a carbohydrate which can bind selectively with the CD44 protein. So, and what is hyaluronan? It is a linear carbohydrate consisting of disaccharide reporting unit of gluconic acid and N-acetyl glucosamine. So we just aim to functionalize our surface, our search nanoparticles with the HA ligand, which can target the CD44 protein, which is expressed in different types of cancer cells. So already I have mentioned that gold nanoparticles is functionalized with the gold thiol interaction. So we have considered the thiolated HA, which is commercially available. So we can see, and also we have considered one control, that is the thiolated PEG. PEG is polyethylene glycol. So this is a control which has no or limited affinity towards the CD44 protein. And HA, this is a targeting which can selectively bind the CD44 protein. So you can see these are the DLS for the without functionalization of such nanoparticles with HA and the PEG. And this is the after the functionalization. There is an increment of the DLS we can found. From this experiment, we can say that our nanoparticles is functionalized with the HA, that is hyaluronan, and the PEG. And also we just measured the zeta potential. You can see this is the bare search nanoparticles, suppose S420 without any addition of the PEG. You can see the PEG, there is a decrease of the zeta potential. In case of the HA, you can also see that there is a decrease in the zeta potential. So this increment of the DLS size and change in zeta potential is an indication of search nanoparticles is functionalized with the PEG and the HA. Then we just did the biological assay. How first we check the biological assay if the HA can bind with the CD44 protein or not through the competitive ELISA test. ELISA is an enzyme-linked immunosorbent assay test. You can see the HA. So there is a decrease in the normalized optical density. This is an indication of the increment of the binding. So we can see with the increment of the HA concentration, the binding is increased. This is the free HA without the functionalization of the HA with the gold nanoparticles. You can see the HA can selectively bind to the CD45 protein. Then we just worked with the HA functionalized gold nanoparticles. You can also see that with the increase of the concentration of the HA search nanoparticles, the binding affinity is increased. Then already I have mentioned that the HA, this is a glycan, that is a polysaccharide. Then we just observed if the change in the length of the polysaccharide effect of the binding or not. We just considered the 10 kilodalton, 250 kilodalton, 1500 and 10 kilodalton. And we find out that there is no effect of molecular weight on the affinity of the HA towards the CD44 protein. Then, so here we can see the binding, but this is not too much binding. So that means HA functionalized search nanoparticles shows the binding towards the CD44. The binding is not too high. Then we just aimed to functionalize or just the search nanoparticles with the liposome, because we know liposome, this is a biocompatible biomaterial, and this is also can be act as a passive targeting. So we just formed a search HA or PEG complex with the liposome using the thin film hydration method. In this method, we just considered the lipid and the cholesterol in a co-solvent organic solvent, that is the chloroform-methanol. We just dried it. A lipid film is formed. Then we hydrated with the search nanoparticles. We sonicated, and the complex is formed. Then the complex is characterized through the TEM, DLS, and zeta potential. You can see these are the TM image of the S420 search nanoparticles PEG. This is S481HA. This is the liposome one. You can see, so whenever the particles is, these are the TM image. So you can see the hydrodynamic size is increased when the particles is not liposomal complex. So that means when the increase in the diameter, this is an indication liposomal complex is formed. And also you can see there is a change in the zeta potential before and after the formation of the liposome complex. This is also an indication of the liposomal complex formation. Then again, we did the ELISA test to check the binding affinity of the liposomal search HA towards the CD44 protein. You can see here now this optical density is decreased a lot. That means the liposomal search HA can bind more than without the liposome towards the CD44. And you can see this, so this is the just comparison. You can see this is liposome search HA, this is the PEG. So from the optical density measurements, you can easily see that the PEG one, which is non-targeting, cannot show any affinity towards the CD44 protein, but the liposomal search HA can bind with the CD44. And also the binding affinity is increased with the increase in the concentration of the search nanoparticles. And you can see, suppose this is the 20 picomolar and this is the 250 picomolar HA. You can see the free HA, just the intensity decreased to 0.5, but only 20 picomolar, the intensity decreased to almost 0.2. That means our liposomal search HA can bind more strongly than the free HA. So we can conclude that liposomal search HA can selectively bind with the CD44, which will help us to distinguish or differentiate the cancer cells or cancer which has the overexpression of the CD44. Before doing the cellular experiment, we just check the cell viability. If our molecule, that is the biocompatibility. So the biocompatibility assay was done through the cell viability experiments. You can see our search PEG and search HA. This is a targeting. This is a non-targeting. Both targeting and non-targeting does not affect on the cell viability. That means these particles are in good biocompatible. Then we also checked the stability. The stability assessment was done through two different experiments. One is the UBBs, another one is hydrodynamic diameter. And we considered the nanoparticles stability in physiological conditions, that is in PBS and serum. You can see minus PBS and plus PBS, that is without PBS and in PBS. You can see there is no change in absorbance happened. And also it is in 1x PBS and 10x PBS. And also you can see our nanoparticles does not affected by the serum. So this is the UBBs. We further confirmed the stability of our search nanoparticles under physiological conditions through the hydrodynamic diameter. You can see there is not significant change in the hydrodynamic diameter happens in PBS and serum. That means our search nanoparticles is stable in the physiological conditions we examined in PBS and serum. We also examined the stability of the search nanoparticles in storage conditions. This is at 4 degrees centigrade at the room temperature. Over the 3 weeks, we found there is no significant change in the search intensity happen if the nanoparticles is stored at 4 degree or even the room temperature. So from these experiments, we figured out that our search nanoparticles is stable in physical conditions and storage conditions over at least 3 weeks we examined. Then we just applied the nanoparticles to distinguish or differentiate the cancer cells. Here we considered the 41 cancer cell. So 41 cell is a mouse melanoma cancer cell. This is mouse breast cancer cell. You can see, so this is S44 to the PEG. So PEG, already I mentioned that this is a non-targeting. You can see there is no search signal is coming out. So that means the PEG1 cannot bind with the 41 cancer cells. 41 is a breast cancer cells. But the targeting on HA, you can see the search signal here. So that means this search signal is coming from the HA. So this HA can bind with the cell lines, which is already has overexpression of the CD44. That means we can easily differentiate or determine the cancer which has overexpression of the CD44 protein. So from this in vitro experiment, we figured out that our search nanoparticles can effectively detect the cancer based on the expression of the CD44 protein. Then we did the in vivo experiment. If we can do the image guided surgery or not. This is the camera image you can see. So first, you can see this is the before removal. So before removal, this is the image. Then we just, already I have mentioned that the physicians are using usually visualization and palpatory. So we just remove the tumor through the visualization. Then we spray our nanoparticles. You can see signal is coming from the just the removal site. That means still now there is some residual marker is present there. Then after second removal, we again spray the particles. We find out the signal is coming. So that means still now there is some residual markers are present there. And then we again just did the surgery. And finally, you can see there is no signal is coming. So that means now this is the complete removal of the tumor from the tumor sites. So that means we can completely remove the tumor using the search techniques. Then we did the ex vivo experiment to figure out if these particles can only just bind with the tumor, not the normal cells. You can see tumor 1 and tumor 2. We consider 2 tumors, liver, heart, and kidney. These are the tissues, normal tissue. So you can see search signal is coming from the tumor 1 and tumor 2, but there is no or negligible amount of search is coming from the normal tissue, liver, heart, and kidney. So that means our search nanoparticles can just bind with the tumor tissues, not the normal tissues. So in conclusion, we can say that we can successfully synthesize the search nanoparticles with low femtomolar sensitivity, and liposomal search complex shows the higher affinity towards the CD44 than the non-liposomal, and this search probe can effectively be used to remove the tumor through the image-guided tumor surgery. This is my current research group. Thank you for the kind attention.
Thank you, sir. Thanks for your enlightening talk. Participants, if you have any queries, please type in the chat box, or you can unmute. You can ask. Or write your feedback on the chat box. So you can stop share screening now. So we can go for a question session if any. So there is a no questions, sir. Only they are putting some amazing application, fantastic session. Very nice section. So you have any queries, please ask now. Okay. So there is a no question, sir. Thank you.
Thank you so much. Thank you all.
Thank
Thank
you
you
so
for
much.
inviting me. Yes.
Yes.
Sir,
Someone,
today-
Sridevi.
There is no available for the group feedback form, sir.
Feedback we will send you, sir. Sridevi, ma'am, you want to?
Yes, sir. Yes, sir.
No. Olgana. Question is there, how to download the JCPDS file? Hello? Are you audible? Any free softwares for XRD? Feedback link post பண்ணுங்க. Atique, are you there?
Yes, I am here.
There is two questions. How to download the JCPDS file, and there is any free software for XRD measurement?
So XRD, I don't understand. Could you repeat, please? So free software.
Free software for XRD analysis.
I did not show any XRD here.
Yes, but the question is there. Sir, kindly share your PPT or some questions is there. Other than gold nanoparticle, can we try any other nanoparticles?
Yes, we can try with the gold, silver nanoparticles also, because usually silver and gold nanoparticles, these two types of nanoparticles are mostly used for the SARS properties, that is surface enhanced Raman scattering properties. But for the biological application, we used to use the gold nanoparticles because this is biocompatible than the silver nanoparticles, we believe.
So any other question? There is no question, sir.
Okay, thank you so much.
Thank you so much. Thanks. You can have some sleep.
Okay.
Thank you. Thanks for your time. Participant, the feedback link will be shared shortly. Please fill the feedback link. So the attendance is mandatory to get the certificate. Please fill the feedback form. Afternoon, we have one session at 3 o'clock. Please join the special session.
Okay, sir.
We have one session at 3 o'clock,
Yes,
3
sir.
p.m.